Hello, everyone. So last time we were looking at the proofs, methods of proofs. Last time, methods of proof. And then we looked at direct proof. So in direct proof, we saw that, we can start with the assumption. Remember, there is always, when you want to prove a conditional statement, there is an assumption, or called also a hypothesis, and there is a conclusion. And we can start with the assumption, and in direct proof we start the assumption, and we do some reasonings or computations in the middle, and at the end we have to reach the conclusion. We also see about the proof by contraposition, and also proof by contradiction. So in both of these methods, proof by contraposition and proof by contradiction, we assume what we want to show, which we call it Q normally, is wrong. In other words, we assume negation Q is right. And then we either try to reach negation P, or we reach a contradiction, which could be either negation P or a contradiction with a mathematical fact, like 2 equals 0, let's say. And anyways, once we have a contradiction, it means negation Q cannot be right, and therefore Q itself must be true. Okay, so the next topic we want to cover is proof of equivalences. Equivalences. So previously we saw about the definition of equivalence of two propositions, let's say P and Q. We called it biconditional statements, if you remember. So we saw that P if and only if Q, right? So read it as P if and only if Q if P implies Q and Q implies P. So basically every biconditional statement, or every if and only if statement, is two statements combined. So if in the exam, let's say you want to prove a biconditional statement, it means you have to prove or solve two problems. Once you have to prove P implies Q, and then you have to prove Q implies P. Okay, so for example, let's say, show that n squared is odd if and only if n is odd. So if you remember last time, we proved both directions, that if n is odd, then n squared is odd, and also if n squared is odd, then n is odd. Therefore, if both statements are true, then that means the statement is an if and only if statement. So just to do a quick review, let me remind you about the proofs quickly. So proof. So usually when you want to prove an if and only if statement, it would be nice if you clarify or specify which statement you are going to prove first and which statement you're going to prove next. Because remember, we have to prove two statements. Once we have to prove P implies Q, and once we have to prove Q implies P. So first, assume that n is odd. Then n is equal to 2k plus 1, right? For some integer k. and therefore n squared will be 2k plus 1 the whole squared. And if you remember, we expanded this as 4k squared plus 4k plus 1, and then we wrote it as 2 times 2k squared plus 2k plus 1, and then that means n squared is odd. So see, this direction is done. Then you can write down like this, that for example, next, suppose that n squared is odd, and so the other direction, right? The other direction, we assume n squared is odd, and we want to show n is odd. And if you remember this one, we can do it with proof by contraposition or proof by contradiction, and the proofs were very similar, whether proof by contradiction or proof by contraposition. So proof by, let's say proof by contradiction. Suppose n is even. If n is not odd, then it has to be even. Then n is equal to 2k for some integer k. And therefore n squared is equal to 4k squared, which is 2 times 2k squared. And this is contradiction with n squared being odd. Okay, so we proved both statements, P implies Q and Q implies P, which is we have proved if and only if statements. Okay, then, so this is for equivalence of two propositions or two statements, P and Q. What about if we have more than two? So now equivalence of more than two statements or propositions. Let's say P1 to Pn. So we say that P1 to Pn are equivalent if P1 implies P2 and P2 implies P3 and P3 implies P4 and Pn minus 1 implies Pn and Pn implies P1. So if all these statements are true, P1 implies P2, P2 to P3, P3 to P4, Pn minus 1 to Pn, and then Pn to P1. So it's basically a cyclic conclusion. So we conclude 2 from 1, 3 from 2, all the way to n from n minus 1, and then we conclude 1 from n. And then this means that all of them must be equivalent with each other. So let's look at an example. Show that the following statements are equivalent. So the first one is n is even. Next one is n minus 1 is odd. Third one is n squared is even. So again, see, we want to prove equivalence of 3 statements. So we can go from 1 to 2, then 2 to 3, then 3 to 1. We have to do a cyclic reasoning, and then so 1 to 2, 2 to 3, and then we go back to 1 from 3. So 1 to prove, 1 to 2, So suppose n is even. So then n is equal to 2k for some integer k. So n minus 1 would be 2k minus 1. If n is 2k, n minus 1 would be 2k minus 1. Now, we want to show n minus 1 is odd. Well, we know that we have to look at the definition of odd. What is the definition of odd? Any number of the form 2 times an integer plus 1. Well, right now I have 2 times an integer minus 1. Can I rewrite this as 2 times an integer plus 1? Well, yes, I can easily do that. I can just write this one as 2 times, let's say k minus 1 plus 1, because then 2 times k minus 1 is 2k minus 2 plus 1 will be 2k minus 1. Okay, so that means n minus 1 is odd, right? Because it's 2 times an integer. K is an integer, so k minus 1 is also integer. So 2 times an integer plus 1. That means n minus 1 is odd. Okay, now what about 2 to 3? 2 to 3, n minus 1 is odd. So if n minus 1 is odd, then I can say that n minus 1 is equal to 2k plus 1, right? For some integer k. So then that means n is equal to 2k plus 2, right? If I take 1 to the other side, and I can take 2 out, 2 times k plus 1. So n squared would be, I want to show that n squared is even. So n is 2 times k plus 1. N squared will be, if I raise both sides to power 2, 4 times k plus 1 squared, which is 2 times k plus 1 squared. See, I want to show n squared is even. Even means what? Means 2 times an integer. Well, I wrote it as 2 times this guy, and this guy, of course, is an integer, right? Because k is integer, so k plus 1 is integer, k plus 1 to power 2 is integer, and 2 times that is also an integer. So that means n squared is even. And lastly, 3 to 1. If n squared is even, then I want to show n is even. Then n is even. So this one we have done many times in the during today and also last lecture. How did we do it? If n squared is even, then n is even. The proof is proof by contradiction. So suppose n is odd. So that means if n is not even, it has to be odd. So n is equal to 2k plus 1 for some integer k. So then that means n squared will be 2k plus 1, the whole squared, which is 4k squared plus 4k plus 1, and that's 2 times 2k squared plus 2k plus 1. That means n squared is odd. And this is contradiction with n squared being even. So 3 to 1 is also done. So we did 1 to 2, 2 to 3, 3 to 1. And that means all these 3 statements are equivalent with each other. Okay, so let's look at another example. So this one is question 34, page section 1.7. So this says, show that these statements about the real number x are equivalent. So the first one is x is rational. Second one is x over 2 is rational. And the third one is 3x minus 1 is rational. Okay, so again, we want to prove equivalence of three statements. So the standard approach is going to be 1 implies 2, 2 implies 3, 3 implies 1. So that's very easy. So let's say proof 1 implies 2. So suppose that x is rational, means x belongs to Q, right? And I want to show that x over 2 is rational. But again, I have to look at the definition of rational, right? So the most important thing that you have to remember in all proofs is that you have to always apply the definitions. So if x is rational, what can I say about x according to a definition of rational numbers? I can say that then x is equal to a over b, right? For some integers a and b with b not equal to 0, right? So definition of a rational number. Definition of a rational number means any number of the form a over b, where a and b are integers and b is not equal to 0. Now what do I want to get at the end? I want to get to x over 2 is rational. So right now I have x equals a over b. I want to get x over 2. Well, it's obvious what we have to do here, right? We have to just divide both sides by 2. So thus, x over 2 is equal to a over 2b, where a and 2b, right, are integers. And 2b is not equal to 0, since b is not equal to 0. So just by dividing both sides by 2, we can observe that x over 2 is also of the form a over b, where a and b, well, of the form, let's say a prime over b prime now, where the numerator a prime is same as a, denominator b prime is 2b, and numerator and denominator are both integers, right? I was assuming a and b are integers, therefore a and 2b are integers, and denominator, which is 2b, is also not 0 because b is not 0. So then that means x over 2 is rational number. So this was 1 to 2, now 2 to 3. So suppose x over 2 is rational. X over 2 is rational means x over 2 is equal to a over b, right? For some integers a and b with b not equal to 0. See, it could look a little bit confusing. Why did we say x over 2 because a over 2b here? And why did we say x over 2 because a over b here? Well, in the previous part, 1 to 2, I started with x itself because that was my assumption. My assumption was x is rational. So I started with x itself. I wrote as a over b, then divided by 2, x over 2 became a over 2b. But here, 2 to 3, I have to start with 2. What is 2? 2 is x over 2 being rational. So I have to start with x over 2 equals a over b this time, with a and b being integers and b not equal to 0. And what do I need to get? I need to get 3. What is 3? 3x minus 1. How can I get 3x minus 1 from x over 2? What type of calculation should I do here? Well, that's easy. You know, I have x over 2. I can first multiply by 2 to get x, and then I can get 3x minus 1 from there. So I can multiply by 2 first. X will be 2a over b. And then I want to get 3x minus 1. Remember, that's what my 3 was. Condition 3 is 3x minus 1 is irrational. So I have x now. Then I can multiply by 3 to get 3x. Going to be 6a over b. And then minus 1. So that's going to be 3x minus 1 equals 6a over b minus 1. That's 6a minus b over b, where 6a minus b and b are integers. Since a and b are integers, right? I was assuming a and b are integers. So if a and b are integers, 6 times a minus b is also integer, right? 6 times integer minus another integer is definitely an integer. And b not equal to 0. Again, by assumption, I had b not equal to 0. So that means 3x minus 1 is a rational number. And then I need to prove 3 implies 1. So suppose that, so 3 implies 1, we have to start with 3. Condition 3, where is condition 3? 3x minus 1 is rational. So suppose that 3x minus 1 is rational. So then that means 3x minus 1 is equal to a over b for some integers a and b with b not equal to 0, right? So our starting point this time is 3x minus 1. Therefore, 3x minus 1 is set to be a and a over b this time. And then what do I want to get at the end? I want to get condition 1. Condition 1 is about x. But right now I have 3x minus 1 and I want to find x. How can I get there? That's easy. I can take 1 to the other side first, right? So then 3x is equal to a over b plus 1, and common denominator is going to give me a plus b over b. So that's 3x. And then just divide by 3. I'll get x equals a plus b over 3b. Where a plus b and 3b are integers, right? Since a and b are integers, and 3b is not equal to 0. Again, since b is not equal to 0. So again, I showed that x can be written as some numerator over denominator, where both numerator and denominator are integers, and denominator is not equal to 0. And then that means x belongs to Q. Okay. All right, so the next thing we want to say, next topic is proof by cases. Proof by cases. The next we study proof by cases. So in some mathematical, or for some mathematical statements, the proof can be divided into a few parts depending on the value or values of our variable or variables. So let's look at an example. Use inequality axioms. A bigger than B implies AC bigger than BC if C bigger than 0 and A bigger than B implies AC less than BC if C less than 0 to show x squared bigger than equal to 0 for every real number x. So in mathematics, we know that we have to prove all the statements except axioms. So axioms are a very few facts that we accept without proof based on our intuition, and then we prove everything else using them. Now, for inequalities, we can accept these two as axioms that if you have an inequality, you can multiply both sides with a positive number and the inequality remains the same. And if you multiply with a negative number, the inequality will flip, okay? So we want to use this to show that x squared is bigger than or equal to 0 for every real number x, right? So we already know that x squared is bigger than or equal to 0 for x squared, in other words, is non-negative for every real number x. But how can we provide a proof? We want to provide a proof using these two axioms. So here we want to use cases because our proof is, we want to prove a statement about x, right? Now, what is x? Is it positive or is it negative? Or is it 0? Well, depending on whether it's positive or negative, our argument will be a little bit different. Therefore, we have to divide our proof into different cases. So that's why we said in some statements, the proof can be divided into few parts depending on the value or values of our variable or variables. Here, we want to prove a statement about x, and depending on whether x is positive or negative, the proof will be a little bit different. So we have to adjust the proof based on the value of x. Therefore, we are going to divide the proof into few cases. So proof case 1, if x is equal to 0, so the easiest case is if x is 0, right? Then x squared will be 0 squared, which is 0. And 0 is bigger than or equal to 0. Remember, I want to show that x squared is bigger than or equal to 0. Well, if x squared is 0, well, 0 is bigger than or equal to 0. So we are done in this case. Case 2, if x is bigger than 0, right? I want to prove the statement about the real number x. Now, this real number x, there's only 3 possibilities for it. It's either 0 or something positive or something negative. Now, if it's something positive, what can I do? See, remember, I'm allowed to use these two properties. So the property 1 says if I have an inequality, I can multiply both sides with a positive number and the inequality remains the same. Well, in this case, I'm assuming that x is positive. So I'm allowed to multiply both sides by x. Then I'll get x times x bigger than x times 0. X times x means x squared. Bigger than x times 0 is 0. So this one by axiom 1 above. And finally, case 3. If x is less than 0, then again I can multiply both sides by x. But this time I have to use axiom 2. Axiom 2 says if you have an inequality, you multiply both sides with a negative number, the inequality will flip. Well, x is right now negative. Why is negative? Because this is my assumption in case 3. So we are dividing the proof into different cases. In each case, I make an assumption about x, and therefore I'm of course allowed to use that assumption during my proof for that case. So case basically here means a possibility, right? So the third possibility is that if x is negative, I multiply both sides by x. Now axiom 2 above says that x times x is bigger than 0 times x, right? Because as we said, x is negative according to the assumption of case 3. And then this means x squared is bigger than 0, right? So again, we are done. See, so we said that if in case 1, we proved x squared bigger than or equal to 0, case 2, x squared bigger than 0, case 3, x squared bigger than 0. So in any case, x squared is bigger than or equal to 0 as desired. So the important thing that you have to remember when you do proof by cases is that your proof has to cover all the possibilities. So how many cases, that's up to you, right? So right now I divided my numbers into positive, negative, and 0. So I had to assume 3 possibilities. But I could say, for example, I could consider 2 possibilities. Let's say if let's say as case 1, I could consider x bigger than or equal to 0, and case 2, x less than 0. You could write it also that way. So let's look at another example. So use the definition of absolute values. So do you remember the definition of absolute values from pre-calculus? Absolute value x is equal to x itself if x is bigger than or equal to 0, and minus x if x is less than 0. Okay, so this is the definition of absolute value x to show that absolute value x is bigger than or equal to 0 for every real number x. So let's say this is part A, and part B. X is less than or equal to absolute value x, again for every real number x. And part C, x is bigger than or equal to minus absolute value x for every real number x. Okay, so let me do part B, for example, and part A and C I'll leave as exercise. So proof A and C exercise. Part B, so we want to show x is less than or equal to absolute value x. Now, what is absolute value x? Or in other words, how can we get rid of the absolute value sign? Well, according to the definition, so you can see that in every problem that we are doing, we are constantly using the definitions. According to the definition of absolute value x is either x itself if x is positive, or minus x if x is negative, right? So I can consider two cases, right? Because I want to get rid of absolute value x, right? So now absolute value x is either x itself if x is positive. So that's one possibility. And the second possibility, if x is negative, absolute value x will be equal to minus x. So let me say case one, if x is bigger than or equal to 0, then absolute value x is equal to x, right? And we have x less than or equal to absolute value x, which is x itself, right? So any number x is less than or equal to itself, obviously, right? So then this will be true. And case two, if x is negative, then absolute value x is equal to minus x. And we have x less than equal to absolute value x, which is equal to minus x. Why is that? So see, case one was obvious, right? Okay, remember my final ultimate goal is to prove part B x less than equal to absolute value x. Now, if x is positive, so that's one possibility, the right-hand side of this inequality will become x itself. So x is less than equal to x itself because any number is less than equal to itself. So that's a trivial or obvious inequality. So case one was obvious. Case two, however, if x is negative, then the right-hand side of this inequality becomes minus x. Now my claim is that x is less than equal to minus x if x is negative. Why is that true? Since x less than, I want to show, what is my claim? What do I want to show? I want to show that x is less than equal to minus x, right? And when will this be true? Just let's do a simple algebra. This will be true if x plus x is less than 0, if I take everything to one side. And this is true if 2x is less than 0. And if I divide by 2, I'll get x less than 0, which is, and x less than 0 by assumption of case 2. So my claim was x is less than minus x. How can I prove this claim? Just if you do simple algebra, some simplification, x less than minus x turns out to be equivalent with x less than 0. But x less than 0 was my assumption in case 2, therefore it's true. And therefore x less than minus x is true as well. Okay. Now let's look at another example. Prove that there is no positive integer n. So this is question 31, section 1.8. Yeah, 31, section 1.8. Prove that there is no positive integer n such that n squared plus n cubed is equal to 100. So why do you think there is no positive integer n that n squared plus n cubed is equal to 100? Well, let's think about positive integers n. For example, 1, 2, 3, 4, right? So for most of them, n squared plus n cubed will become a big number, right? For example, even if n is 5, 5 squared plus 5 cubed, 5 cubed is already 125, plus 5 squared, 25. for sure bigger than 100. If you use a bigger number like 6, that left-hand side becomes even bigger, right? So for most of the positive integers, left-hand side is already bigger than 100. And therefore, that means, those values of n cannot be a solution for this equation, because for those integers, left-hand side is bigger than 100, and therefore this equality cannot hold. Okay, so let's consider our cases this time based on how large n is. If n is large enough so that the left-hand side is already bigger than 100, then we have a guarantee that those values of n are not a solution for this. And if n is not large enough so that left-hand side is bigger than 100, well, then we can check it manually. Just plug the value of n and see whether it satisfies the equation or not. If it doesn't satisfy, it means it's not a solution for this equation. Well, okay, so how large now? What is the cutoff for my cases? When can I say n is large enough so that left-hand side is bigger than 100? Well, we just said that if n is 5, for example, left-hand side is already bigger than 100. What about 4? If n is 4, as left-hand side becomes, 64 plus 16, that's less than still 100, right? So 4 is still not large enough, but 5 is large enough, right? So the cutoff is 5. So I can say case 1, if n is bigger than equal to 5, then a left-hand side, which is n squared plus n cubed, will be bigger than equal to 5 squared plus 125, right? 5 cubed, which is 125, equals 150. And that's bigger than right-hand side. Thus, for such values of n, left-hand side will not be equal to right-hand side. Right-hand side is 100, right? 150 is bigger than 100. So for n bigger than equal to 5, left-hand side becomes bigger than equal to 150, which is for sure bigger than 100. Now, what about case 2? Well, case 1 already covers most of positive integers, right? Positive integers means what? Means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to infinity. Well, most of them are bigger than equal to 5. Only few of them are not bigger than equal to 5. Which ones are not bigger than equal to 5? If n is equal to 1, right? Or 2, or 3, or 4. Well, we can just check manually whether these 4 values are solution for this equation or no. If not, if none of them are solutions, well, in case 1, we didn't have any solution either. So overall, we won't have any solution. So if n equals 1, then left-hand side becomes how much? I'm talking about left-hand side of this equation. N squared plus n cubed. If n is 1, is 2, not equal to 100. If n is 2, left-hand side becomes how much? 2 squared plus 2 cubed. 4 plus 8 is 12, not equal to 100. If n equals 3, left-hand side becomes 3 squared plus 3 cubed, 9 plus 27. And 36, not equal to 100. And if n equals 4, left-hand side becomes 16 plus 64. That's 80, not equal to 100. So we don't have any solution for our equation, whether in case 1 or in case 2. And that's what we wanted to show. We want to show there's no positive integer, meaning that this equation has no solution in the set of positive integers. Now, my question is, what about if I remove the condition that is mentioned here? So this particular question was asking you to show that this equation has no solution in the set of positive integers. There's no positive integer n with this property. What about if I remove the positive integer condition and just consider n to be integer? If I consider n to be an integer, not necessarily a positive integer, do you think this equation still has no solution? Or do you think there could be some solution in that case? So let's see. Does the equation n squared plus n cubed equals 100 have any solution in the set of integers? Well, the main argument that we used in the previous example was that if n is bigger than 5, then left-hand side becomes bigger than 150. But if n is an arbitrary integer, meaning that it's allowed to be negative, well, then I cannot say that in most cases left-hand side is bigger than 100, right? For example, let's say if n is minus 10. If n is minus 10, how much is the left-hand side? Minus 10 squared is 100, minus 10 cubed is minus 1000. Minus 1000 plus 100 is minus 900. And minus 900 for sure is not bigger than 100, is less than 100. So what type of argument do you think we can give this time? So the main argument was based on the left-hand side bigger than 100 in the previous example. It's not valid anymore. For example, as I said, for n equals minus 10, left-hand side is minus 900, which is less than 100. So what type of argument do you think we can give this time? So this time we are going to give an argument based on the absolute value of left-hand side compared to right-hand side. So because, for example, we just said for n equals minus 10, yes, left-hand side becomes minus 900, which is less than 100. But in absolute value, minus 900 is 900, which is bigger than 100. So still, I can give a similar argument to previous example, but this time I have to make an argument based on the absolute value of left-hand side, meaning that I want to say that the left-hand side in absolute value is bigger than 100, again, for most of the cases. And in few cases might be less than 100, and I can check manually in those cases. So let's see how we can do that. So the answer is no. So let's see why. Proof. So left-hand side is equal to n squared plus n cubed. I can write this one as n squared times 1 plus n. N squared times 1 plus n. Now let's consider the absolute value of left-hand side. Absolute value of left-hand side is absolute value n squared times 1 plus n. And this is same as n squared times absolute value 1 plus n. Right? Which is bigger than equal to n squared if n is not equal to minus 1. Right? See, n squared times absolute value 1 plus n means n squared times an integer. times a non-negative integer. Now, if that non-negative integer is not 0, it means it's at least 1. So a number times a positive number times a number which is at least 1 becomes bigger than equal to original number, right? So if you multiply a given number with a positive integer, you get something bigger than or equal to the original number, right? You cannot get something smaller. So I have n squared times a non-negative integer. Non-negative integer means either 0 or something at least 1. If it's not 0 means at least 1. So something times some positive integer times something at least 1 becomes bigger than equal to original number, right? For example, 6 times 1 is 6, bigger than equal to 6. 6 times 2 is 12, bigger than equal to 6, and so on. So, and 1 plus n is non-negative, is non-zero, as long as n is not minus 1. Okay, so only in the case of n equals minus 1, I can check manually, as we said. But other than that, the left-hand side become bigger than equal to n squared, and n squared is bigger than 100 if, okay, so let me write it this way. So for n equals not equal to minus 1, absolute value left-hand side is bigger than equal to n squared, which is bigger than 100, which is right-hand side. Right? Or absolute value right-hand side. If n is bigger than, n in absolute value is bigger than 10. Right? If absolute value n is bigger than 10, n squared will be bigger than 100. So for such cases, for such values of n, absolute value left-hand side is not equal to absolute value right-hand side, because we just said absolute value left-hand side is bigger than absolute value right-hand side. And that means left-hand side is not equal to right-hand side. And that means our equation has no solution for such values of n. So this was basically our first case, right? So case 1, I can say. Case 2, if absolute value n is less than equal to 10. Okay, see case 1, if absolute value n bigger than 10 and not equal to minus 1. Well, if absolute value n is bigger than 10, automatically n will be not equal to minus 1, right? So I just need to consider this one as my condition in case 1, absolute value n bigger than 10. Right, so this is the condition of case 1 is absolute value n bigger than 10. Now, case 2, absolute value n less than equal to 10, right? Because in case 1, we assume absolute value n bigger than 10, and we assume n is not equal to minus 1. But like I said, once you assume absolute value n bigger than 10, you're automatically assuming that n is not minus 1 either. So that's the assumption in the first case, and the assumption in the second case is absolute value n less than equal to 10, right? So any integer that you consider in absolute value is either bigger than 10 or less than equal to 10. So case 2, if absolute value n less than equal to 10, i.e. if n is equal to minus 10 or minus 9, or minus 8, 0, 1, 9, or 10. So there are 20, how many numbers here? 21 numbers. So for these cases, for these values of n, check that n squared plus n cubed is not equal to 100. Okay, so in case 2, which means n is one of these 21 values, still our equation has no solution. Okay. So in total, it was more complicated, compared to previous example where we're assuming that n is positive integer. This time we assume n is integer. So case 1 was absolute value a number bigger than 10, case 2 less than equal to 10. This one we had 21 numbers, so it's a little bit longer as well. For 21 numbers, you have to check one by one that these are not the solutions for our equation. Right, so for example, if n is minus 10, you can check, right? So 100 plus minus 1000, right? It's minus 900 and so on, which is not equal to 100 and so on. So for n equals minus 9, you can check. N equals minus 8, you can check. And for none of these values, the equation holds. So in total, the equation has still no solution. Even if I assume that n is an integer rather than being a positive integer, still the equation has no solution. Okay, so this was another a little bit more complicated example of proof by cases. Now, the next topic we want to look, so about the existence proofs. Existence proofs. Existence proofs and uniqueness proofs. So these are the next topic. So in mathematics, we are always interested about existence of a solution or of an object of interest, and also the uniqueness. For example, let's say in the topic of, for example, differential equations. So this happens in everywhere in mathematics. For example, differential equations. Given a differential equation, we want to know whether that differential equation has a solution or no. And if it has, does it have only one solution, meaning a unique solution, or does it have more than one solution? So for existence proofs to prove existence of an object of interest in mathematics.